We're going to look at improper integrals. You've done a lot of integrals. They all had numbers in them. They had functions. But there are some types of integrals that are called improper because of one thing or another. And the one we're going to look at is the integral from a to infinity of f of x dx. The infinity is not a number. It's just increasingly large numbers. So we have to figure out how to deal with that and how that can be. Well, if you think about this as area, because we just did area under a curve, so I have this curve here, and we know that as it moves out, this curve, let's say it's one that has a horizontal asymptote and levels off. But maybe we want the area under the curve from this point forever. Is there an area? Turns out, depending on the curve, sometimes there is actually an upper bound and the area does approach a number. And in other cases, it just continues to get larger and larger. So the area under a curve, the A value just stays here, but the B value keeps getting bigger, and we have to work with limits. So this integral has to be written as the limit as B approaches infinity of the integral from A to B of f of x dx. And we do our regular definite integral, except we have an upper bound that's going to be a B and a number for A. Sometimes we don't use it as area. It could be something, an amount of money that if you have an investment and it continues in the long run implies it keeps going forever, although we know things don't really keep going forever. And other types of information or wording that indicates something that just keeps going. So let's look at an example. Integral from 0 to infinity of e to the negative 0.05t dt. And I want to evaluate this integral, see what it comes out to be. I have to rewrite it. Limit as b approaches infinity of the integral from a to b, 0 to b, of e to the negative 0.05t dt. Now, how do I go about doing that? Well, I have to do an integral from 0 to b, means I have to evaluate this. You know the integral of e to the x is e to the x. Have to remember how to do an integral with an exponential function, and there is a possibility of u substitution, but there's also a shortcut rule. When you do u substitution, the whole exponent is u. U equals negative 0.05t. du would be the derivative, which is negative 0.05, and you multiply by dt. So we'd have to put in a constant and take out a constant to use u substitution, which leads us to a rule, a shortcut rule. The rule that we'll use is the integral of e to the kt dt is equal to 1 over k times e to the kt plus c. Let's see how this works, and it will work exactly the same as doing u substitution, but it's shorter, so it's an additional one you can memorize. Let's go with this limit. Limit as b approaches infinity. If I use the shortcut rule, my k is negative 0.05 times e to the kt, negative 0.05t, and it goes from 0 to b. So I've used a shortcut rule for the antiderivative, and now I need to plug in my numbers. Limit as b approaches infinity. I think I'll keep this as a constant in front. E to the negative 0.05 times b minus e to the negative 0.05 times 0. Now, e to the 0 is 1. But what about this piece? Well, if we put this negative exponent lets us go to the denominator with a positive exponent. And if I start picking bigger and bigger and bigger numbers for b, e to the first, e to the second, e to the third, e to the fifth, these numbers on the bottom get extremely large. E to the 0.05b approaches infinity. It's huge. But it's in the denominator. So that means this whole denominator, the whole fraction approaches 0. So what I really have is 1 over negative 0.05 times negative 1. So 1 over negative times the negative makes it a positive. 1 over 0.05 is 20. So multiply that by that and I get 20. What that tells me is that, like the area problem we were thinking of, it is approaching 20. That is, think of it as an upper bound. And so we say it converges. The integral converges to 20. Here's another improper integral. It goes from 2 to infinity of 1 over 3x dx. A couple things to watch out for here. The first thing we want to do is make our limit as b approaches infinity of the integral from 2 to b. This is a 2. And this 1 over 3x, be careful with that. This is 1/3 times 1 over x dx. You don't want to move the 3. If you want to pull the x up with the negative exponent as x to the negative 1, the 3 has to stay on the bottom. Really, the integral of 1 over x is one of our basic rules. Limit as b approaches infinity. I could move the 1/3 in front of the integral from 2 to b of 1 over x dx. And that's the natural log. So I have the limit as b approaches infinity of 1/3 ln absolute value of x, and it goes from 2 to b. That was nice and short. 1/3 ln of b, and I really could just use parentheses because I'm approaching positive infinity, and so I know that the numbers that go in there are positive, minus 1/3 ln of 2. Now, b has to approach infinity, so you could check numbers like natural log of 1,000, natural log of 10,000, natural log of 100,000. Natural log increases but slowly, and so you can put in really big numbers, but eventually you'll see that it just keeps increasing. So this whole natural log part also approaches infinity, and when you subtract off negative 1/3 ln of 2, that's nothing. And so this integral, this limit, would equal infinity, which means it doesn't have an answer, a particular number. But we know where it goes. It keeps getting bigger and bigger, so we say it diverges. In this lesson, we began to talk about an income stream that is a continuous income stream. In particular, here we'll talk about how to find the total change in that income stream. The stream could be that you receive a payment each month or each year for a certain number of years, or long term, or you invest the same amount each month or each year or each quarter, so that there is the same amount invested at different times on a regular schedule. We assume that this investment will be put in an interest-bearing account. But all we're interested in this lesson is the total change in the income. Now, if you have $10 per month that you're investing, for 10 years, if it's over a time period of 10 years, the easiest way to figure this out would be, say, $10 each month, 12 months in the year, which would give you $120, and then for 10 years, you'd take your 120 and you'd multiply it by the 10 years, and you'd have $1,200. That's just the investment. This does not take into account the interest and the account you put it in, anything like this. This is the value of your income stream or your investment stream for 10 years if you put in $10 each month. But it's possible that your income stream will vary over time. If it's an income stream, especially for investing, people tend to stay the same for a certain period of time and then maybe increase. But you can't do this if you've got a function that represents what your income stream or your investment stream is. So let's look at an example of a problem like that, realizing that another way to do this for your total change, let's see, put that up here. To show you how this one will work first, the total change, and we call it in income, but like I said, it could be investment, is the integral from A to B of whatever the rate is over time. This was $10 per month that you were investing for 10 years, so my rate would be $10 per month. However, if I'm going for 10 years, my rate needs to be a yearly rate, which in this case would be 120 dt. If you do the antiderivative of that, 120t from 0 to 10 gives you 120 times 10, which is the $1,200 that we already found just by multiplying. But sometimes it is a function of t and not a constant, so we'll definitely have to look at a more complicated version now. The rate of the receipt of income in the problem was in the form of a function, 30,000 plus 1,000t, and that was paid each year. It was then invested at an interest rate of 7%, annual rate compounded continuously, so the R value would be 0.07 for 10 years. Now we saw that the formula for total change in income was equal to the integral from A to B of the rate dt, just the rate of receipt of income. There's nothing in here that indicates we need to use this interest rate. That would be necessary if we needed to figure out what the total interest was or the amount of money involved. But for the total change in income, which is all the question asked for, this is the formula that we use. So we have the integral from 0 to 10, because it was for 10 years, of 30,000 plus 1,000t dt. Antiderivative of a constant would give us 30,000t plus 1,000. Antiderivative here, t squared over 2 from 0 to 10. Put in the 10. Put in the 0, we just subtract off the 0. So put all this together and add everything up, and we'll have, let's see, let me get my zeros in here right. How many zeros? 1, 2, 3, 4. 1, 2, 3, 4, 5 zeros. Plus, that's 50. Gives us $350,000. And so that is the change in income, the total change in income over 10 years. We're going to continue talking about a continuous income stream, and now we're going to look at the future value of a continuous income stream. There's a lot of detail in the lesson about this, but basically the future value of an income stream is the total accumulated value of the stream, which was the investment, and the earned interest. So all of that together makes up the future value. R of t is the rate of receipt of income, exactly like it was when we looked at the total change. It is invested at an annual interest rate because now we are interested in the earned interest, which is compounded continuously. You are very familiar with A equals P to the RT. The amount that you have in your account is the principal investment times E to the RT, where R is the annual interest rate, and this is compounded continuously. But this assumed one single investment P, and then it grew in the account. That's not true anymore. Now our future value has a lot more detail because it has to be both the income that's put in at different times. It's the integral from A to B of R of T, that's the rate of receipt, multiplied times E to the R times B minus T. So it's similar, but it's different because we have to account for amounts of money that are invested periodically and are not there for the whole entire time length. So let's look at an example to see just how this is going to work out. In the problem we just saw, the question said how much interest was earned. We were told that $50,000 was invested per year for 10 years at 5% interest rate compounded continuously, and 5% is an annual rate. So when we use our future value formula, we want to be sure that the time units match, and it's $10,000 per year for 10 years, and that's an annual rate, so all the time units are in years. So our future value is equal to the integral from 0 to 10, 50,000 per year, E to the interest rate 5% becomes 0.05. B is the upper bound, that's 10, minus T dt. And we evaluate the integral. I'm going to simplify different things first as we go. People work this a little bit differently, but I have some things I like to do with it. Pull my constant in front, 50,000 integral from 0 to 10. Now let's simplify this exponent. E to the 0.05 times 10 gives me 0.5 minus 0.05t dt. And I'm going to pull this exponent apart. You could start right here to integrate by using U substitution on that exponent. I tend to do a little more work with it first. Let me show you. E to the 0.5 times E to the negative 0.05t. You're more comfortable probably with going from this step back up here. Two things with the same base that are multiplied, you add the exponents. So if you put the exponents together, it goes back up there. But this piece here is a constant. So I have 50,000 times E to the 0.5 times the integral from 0 to 10 of E to the negative 0.05 dt, and I can use my shortcut rule for integration. So I do that, I have 50,000 E to the 0.5 times 1 over negative 0.05, that's my constant K, times E to the negative 0.05t, and we go from 0 to 10. Now we've got to figure out how to evaluate this integral. That's going to require a new page. The upper bound 10 goes in first. I'm going to group all of my constants together. So my future value is 50,000 times E to the 0.5 over negative 0.05. And I put in my 10 for T, E to the negative 0.05 times 10, minus E to the negative 0.05 times 0. All my constants in front. I tend to do the constants at the end to be sure that I have, this is really shorter than the whole string of decimal places you need to use when you multiply by something with 4 zeros. E to the negative 0.5 minus 1. So, E to the negative 0.5, you put your numbers in. Put all these decimals in here, and remember you need to use a lot of decimals because we are multiplying by something with 4 zeros in it. You do all that and multiply it all out, and you get, let me think, I forget. Oh. Here we go. $648,721.27. Okay? But that's not the question. No, that doesn't answer the question. The question said, how much interest was earned? This is the future value. Okay, future value is the investment and the interest. So if I'm looking for the interest, I have to go back and say, let's take this $648,721.27 and subtract off how much was invested. Well, what was invested was I left a zero off there, didn't I? $50,000. Yeah, I got it here. $50,000 each year for 10 years. So I have to subtract off, I think I'll do that under here, 50,000 times 10, 1, 2, 3, 4, is going to be 5 zeros. And I subtract that. 1, 2, 7, 8, 4, 1. There was $148,721.27 of interest earned. Added back to the total change in the income, the invested amount, gives us the $648,721. Our formula for future value involves a rate of receipt of income, time constraints, an interest rate. Usually your time limits are years, and the interest rate is always an annual rate compounded continuously. That means everything needs to be in years. The rate of receipt of income needs to be in years. For example, if you have lottery winnings that you want to get over a long time period, and this comes from an example of the lessons, that's a 6. If you have $360,000 and you want to divide it up and find out information about it, if you use your future value problem or a different problem, it has to be in terms of a year. So this R of T value here would be 12,000. Because you have to, 30,000, because you have to divide by 12. You divided by the wrong thing. Divide this by 12 to get $30,000 per year for 12 years. Over 12 years. And the 30,000 would be your R of T. If you have investments that you're making and you invest $50 a month, then if you want to find out a future value of that investment, first you have to get R of T, which would be 50 times 12. So your R of T would actually be $600 per year. So that your times always match in your formula. So check out these examples and similar ones in the lessons. Now we're going to look at a more complicated example. The problem we just looked at had an R of T, rate of receipt of income, that looks like we really already have the problem because it's got an E in it. However, this really is just the R part. We still have the rest of that to put in order to find the future value for the next 9 years. So the future value is 80 e to the 0.15t times e to the r, which would be 0.08, times 9 minus t dt from now for 9 years. So this is going to require some more simplifying and combining terms. I will pull out my 80 because it's a constant from 0 to 9, e to the 0.15t And now let's simplify this exponent. 0.08 times 9 would be 0.72 minus 0.08t dt. I'll split these up so that I'll pull out in front this part that will be the constant part. 80 e to the 0.72 times the integral from 0 to 9 of e to the 0.15t times e to the negative 0.08t dt. So I split this up into e to the 0.72 times e to the negative 0.08t, pull the constant piece in front, and I have this left. Well, now I have two things multiplied that have the same base. I need to combine the exponents. 80 e to the 0.72 times the integral from 0 to 9 of e to the 0.15 minus 0.08 gives me 0.07t dt. And notice it is now a positive exponent. So we have to work out the values for that. 80 e to the 0.72 times 1 over 0.07 when I do the antiderivative, e to the 0.07t from 0 to 9. We plug all the values in. So let me go back up here. e to the 0.72 e, 20e over 0.07 times e to the 0.07 times 9 minus e to the 0.07 times 0. Don't forget that gives you a 1. Plugging in the 0 doesn't give you a 0. So when you find out all of your values, put everything together up there, you should end up with 2061, and the units here were millions of dollars. So that would be all the future value, the invested amount in its strange exponential form, and the interest rate all combined end up to be this for this particular problem. Now we're going to look at the present value of an income stream. The present value is the amount you would deposit today. You would think of that as your P, your invested amount, in a lump sum, in an interest-bearing account that would equal what you would get from the income stream over the same length of time. So that an income stream deposits amounts yearly over a time period, and each one earns interest at over a different length of time. But the present value means, imagine if you could put in one lump sum, leave it in the interest-bearing account over that same time period, what would that lump sum be? That's your present value. Similar equation, the present value formula is similar to future value. Integral from A to B. I'll say 0 because we're going to pretend like the present is always 0, right? Times 0 when you start. Of a rate of receipt of income, R of T, times the E to the R times, in this case, 0 minus T dt. We consider the present to start at 0. You could say this is A if you were talking something else, but for this course, it's always going to start at 0. So the formula looks just the same, especially if I've left the A here, and we put A here. This will simplify, and we'll see how in an example just now. Our problem is a small business that generates $120,000 annually in rent. It's rental income. If it's invested at 6% over 20 years, they'll have a future value amount of what that business is worth. Well, they want to sell the business, so we need to figure the present value so we know how much they should ask for the business. So the present value formula says that we start at 0 and we go over our time of years, 20 years. The R of T is the annual rate of change of the income, 120,000, times e to the interest rate 6% becomes 0.06, and we have 0 minus t dt. Pull out the 120,000 from 0 to 20 for the integral, and we have e to the 0.06 times 0 is 0 minus 0.06 times t. So this formula is usually much simpler than the formula for present value, future value. So here we go, 120,000. Take the antiderivative of this. I'll have 1 over negative 0.06 times e to the negative 0.06t from 0 to 20. 120,000 over negative 0.06, I'll have e to the negative 0.06 times 20 minus e to the negative 0.06 times 0. Remember, e to the 0 is 1. Let's make my marks match. Do all of your multiplication to come up with the present value of the business, which should be about $1.4 million.